So let us start with the another example. A flywheel of mass 10 kg and radius of gyration 0.3 meter makes torsional rotations under a torsion spring of stiffness 5 Newton meter per radian. A viscous damper is fitted and it is found that the amplitude is reduced by a factor of 100 over any two complete cycles. So this is the important part. We'll see the significance of this. We have to find out the damping factor zeta, damping coefficient C, and periodic time of damped oscillations. So let us write down the data first. So this is the case of torsional oscillations. Mass is 10 kg. Radius of gyration capital K is 0.3 meter. Then torsional stiffness is 5 Newton meter. 5 Newton meter per radian. Now this is the important part. As two complete cycles are given, take n is equal to 3 in our formula. So x1 upon xn. So that n term is 3. If it is given that as 4 complete cycles, then we could have taken x1 upon x4. If it is 3 complete cycle, we could have taken x1 upon x4. So here 2 complete cycles are given. So take n is equal to 3. So x1 upon x3 is equal to 100. Now we know that logarithmic decrement is 1 upon n minus 1. So this value of n just now we have seen it is 3 log of x1 upon xn. Substitute the value of n that is equal to 3. So we can say that it is 1 upon 3 minus 1 log of or ln of x1 upon x3. So 1 upon 2 log of x1 upon x3. Value of x1 upon x3 is nothing but 100. So this is 1 upon 2 ln of 100 and that value comes out to be 2.302. So this is the value of logarithmic decrement. Now zeta is equal to delta divided by square root of 4 pi square plus zeta square. So substitute the values of delta. Delta we have calculated 4 pi square plus delta square. So after substituting these values, we'll get the value of zeta as 0.344. Now we'll compare the linear system and torsional system. So for linear system, we have already seen that zeta is C upon Cc. So C upon Cc is nothing but critical damping coefficient, that is 2 root Km. But in our case, we are having the torsional system. So for torsional system, zeta is instead of C, it will be Ct. Instead of Cc, it will be Cct. T for torsional system. So value of Cct, that is critical damping coefficient. In the linear system, it is 2 root Km. Over here, replace this K by Kt and M by I. So first we'll calculate the value of mass moment of inertia, that is mk square. So m is 10, k is 0.3 and square of that. So it is 0.9 kg meter square. Now substitute this value in the equation of zeta. So zeta is equal to Ct divided by 2 root Kti. So this was our previous equation. This is the equation in which we are now substituting the value of zeta. So Ct you can cross multiply by this term. So you will get the value of Ct as 0.344 multiplied by 2 square root of 5 multiplied by 0.9 and you must get this value. So check this particular value. The unit is Newton meter second per radian. Now again for linear system we are having omega n is equal to square root of k by m. Then for torsional system it will be square root of kt upon I. So kt is 5 and I is 0.9. So you'll get the natural frequency for torsional system as 2.357. Now damp frequency is omega n square root of 1 minus zeta square. Omega n just now we have calculated, that is 2.357. Zeta is also calculated as previously as 0.344 and square of that, and we'll get the value of omega d as 2.213 radian per second. Now omega is equal to 2 pi f and therefore omega d will be equal to damped frequency and damped angular frequency will be equal to 2 pi multiplied by fd. In place of frequency you can substitute 1 upon time period. Transfer this td on this side and omega d on this side. So we'll get 2 pi upon omega d. So substitute the value of 2 pi divided by omega d is 2.213, which we have already calculated. So that 2 pi divided by 2.213, we'll get the value of time period as 2.839 seconds.